Yep. Yeah, Avik, we're going to start. I'm going to make a quick introduction and after that, you'll be free to go. Bon, et bonjour à tous. Merci d'être présent pour ce finalement premier minimap de la saison. Vous excuserez un petit peu la voix nasillarde et l'esprit un peu malade, mais je suis sur la fin. Et qu'aujourd'hui, on a le plaisir de recevoir le professeur Avik Bhattacharya de l'Institut indien de technologie de Bombay, qui a accepté, malgré l'heure tardive pour lui, plus de 10h30 du soir, de nous parler. Donc Avik a réalisé sa thèse de doctorat en France et il est venu travailler quelques années au Centre canadien de télédétection, fait qu'il il ne méconnaît pas nos professeurs ici, Ramata et Khalifa. Et aujourd'hui, ses recherches se concentrent essentiellement sur la polarimétrie radar à synthèse d'ouverture et ses applications de télédétection dans les études qui peuvent être liées à l'agriculture, la cryosphère, l'urbanisme ou encore la planétologie. Donc Avik va nous en dire un petit peu plus d'ici quelques minutes. So Avik, you may share your screen and start whenever you're ready.
Merci beaucoup, Nicolas. So, is my slides visible?
Yes, it's perfect.
Okay. Okay. Thank you very much for the invitation. Well, it's a pleasure to be here. Unfortunately, my voice is not very proper. I'm suffering from a throat infection, but I'm very excited to be a part of this conference. And thank you very much for the introduction, Nicola. Well, I don't speak French very well. I do understand it. I've spent many years in France and in Canada. So I must understand more than what I should now, but unfortunately, it's not so. I'll be talking more or less about some general aspects of radar polarimetry in which I work. And I lead the group of Microwave Remote Sensing Lab at the Center of Studies and Resources Engineering at IIT Bombay in Mumbai. I'll be giving a very brief introduction. I'm not sure when people, all of you are in the domain of microwave or radar polarimetry or not, but quickly going through. So talking about a little bit of SAR and polarimetry basics, some basic target characterization concepts. I'll just talk about some of the ones which have been existing for a long time, very popular, and some of the ones which have been recently introduced and gaining popularity very quickly. And at last, I'll talking about some of the applications and tools developed by our lab in collaboration with various other labs around the globe. So we're talking about the basics, of course, going very quickly through this, that we all know that we measure radar, which we measure is the backscatter coefficient. What we measure is in the normalized backscatter cross section, which is measured in terms of the energy received by the sensor or the energy scattered by an isotropic scatter. So we typically talk about some of the backscatter coefficient ranges for different kinds of targets for Earth observation. We have very high, we say that it is kind of a very strong scattering from man-made targets, slope towards radar. With high, we talk about roughly rough surface, dense vegetation, and so on, and going to very low backscattering from smooth surface because everything is mostly forward scattered. So this is just a typical understanding of when we just look into the backscatter values measured. It may not be always true. These are some of the starting points. Why radar remote sensing? Of course, we have been always asking. We know that some of them are very true, that its covers provide wide swath coverage, all weather monitoring. We get a large volume of data for this new upcoming and existing dual polarimetric SAR data. We are exploring a lot of processing chains or different kinds of applications, especially we have been working on a lot on agriculture. And of course, the new generation dual and compact polarimetry will revolutionize the way we look into the systems or how we measure the data, and of course, then developing new algorithms which will provide uh, many ways of looking into classification, parameter estimation, and many such properties. Now, going through with why radar remote sensing is very important, I'll just give a kind of an example of why it is very useful for an Indian context where I come from. I just show you some of the images of Sentinel-2 false color composite image over an area which is in the southern part of India. This is called the rice bowl of India. It's entirely covered with paddy cultivation. As you can see that almost all the images in uh, this time frame is all covered with clouds. So we hardly see anything on the ground. So this is where it's very important, because this season, which is called as the Kharif season, it spans from June to October, and it starts with the advent of the southwest monsoon season. We see that the Sentinel-2 optical is cloud covered, whereas we see a VV polarization from the Sentinel-1 image provides us with information on the backscatter coefficient. This is exactly the area from what I'm talking about. I'll just give you an example of first one is the poly RGB color composite of this area. And the next one is the Indian satellite, the RISAT image, and it's formed by a false color composite from a decomposition. So this is how the area looks like, and this is why it is so important for us to utilize radar remote sensing data and extract information from them for various applications, from going from prop type monitoring to also going into retrieval algorithms. We see temporal variation of this backscatter intensity for different polarization modes, for different crops. This gives us the first-hand information of what exactly would we expect the kind of backscatter temporal variation over different kinds of crops in different polarization of an HH and VH and a VV. This provides us information about the backscatter coefficient, which then can be used for various different applications. But this is what we are measuring, only the intensity. Now, what about any other properties which are intrinsic to the electromagnetic spectrum? And here comes what we utilize a lot is the polarization state of the wave. Polarization of a wave we know is the locus of the electric field as it traverses in space. In this case, we see that there are the horizontal polarization and the vertical polarization. And this is exactly what we use as another property, as an intrinsic property, apart from there are other properties in wave, interference, and diffraction. Polarization is used in remote sensing. And this gives us an opportunity to extract valuable information. What we start with is we start with the polarization ellipse. We have the components of the electric fields in terms of the EX and the EY. We do not have any component in the EZ because the transverse electromagnetic. And what we can find out is that it simply gives us the equation of an ellipse, which tells you about the instantaneous properties of the wave, the characteristic in terms of the polarization ellipse. Sorry. Utilizing this, what we try to understand is from a radar system which utilizes polarization are two different types. We talk about the dual pole system, the Sentinel-1 type of system, where we talk about this and we call this as wave polarimetry. And as can be seen, that we have one transmit polarization. We are measuring the co and the cross. The measurement is in terms of what is called as the Jones vector, a 2x1 vector. So this is a typical system, which is a dual pole system. Now, how it changes when we have a full pole system. When we have a full pole system, what we study is the scattering polarimetry. That means from one state, we are on one side, we are talking about only in terms of the wave nature. On the other hand, we are talking about from the target point of view. And here the things are slightly different because here you are transmitting two polarization, two orthogonal polarization, X and Y, and measuring the co and the cross and simultaneously the other. So it's actually two column of the Jones. And this is what is the Sinclair matrix, or the 2x2 complex scattering matrix. This is the starting point of all dual and full polarimetric SAR data analysis. A typical example of how does it look like. This is a single look complex image of an area of San Francisco, very well known in the literature. If we try to zoom into an area and see what we look into it, so we see that the SHH component, the intensity of it, it shows the bridges. Here there is one bridge, but we see three of them because of the echoes which we have. Echo from the bridge, from the water, and the bridge, from the bridge and the water. And hence we also see them in terms of the real and the imaginary part. We don't see much information as such over here. This is for the HH image. We see that for the VV image, slightly different information, and the same we can see for the HV information. So this corresponds to 1 pixel of a full polarimetric SAR image, a 2x2 complex matrix. Now, with the advent of technology coming into picture, we see many different technologies which are there, and some of them will be available soon in the future. So we have the polarimetric SAR, POLSAR, we have interferometric, we have polarimetric, interferometric, polarimetric tomographic SAR, and polarimetric time SAR. Now, quickly going into how they are defined. For polarimetric SAR data, we are only trying to extract information from a measured Sinclair matrix, scattering matrix, only at one time. From this, we can find out many types of scattering characterization, which can then be useful for classification and many other characteristic information extraction from targets. Going to interferometric, we just have from two time stamp, and we are looking from two vantage points, the sigma naught information, the intensity along with the phase information, which then allows you to compute different kinds of topographic information. The polarimetric interferometric SAR is a combination of both. Unlike what we saw before, that we had only one channel information, the intensity and the amplitude over here, here we measure the full polarimetric information in terms of the S matrix over here. And then we utilize them again to find out not only the height information, but also characterize the scattering properties also. So the scattering properties along with the height information. We go to the polarimetric tomosar, which measures polarimetric information from different points of view, so slices of information, which then allows you to again to construct height again, but also finding out the scattering information at various different scattering phase centers. The polarimetric time series information is measured is the same, the scattering information of the same scene over different time frame. This is important for different kind of characteristic of time series analysis, which are very, very important, of course, for agricultural application and for cryospheric application. So this is where we are now. Well, we'll look into more into the radar polarimetry in this part of the lecture. Radar polarimetry, which deals with the full vector nature of the electromagnetic wave. So this information, the backscatter information, is a function of many variables, and it's also dependent on the transmit and the receive polarization. And of course, you can find a lot of applications for Earth observation and also nowadays for planetary observation also. Moving into what is coherent and incoherent scattering. So we know very well that if you have a completely polarized wave for a coherent case, then the 2x2 complex scattering matrix is enough to characterize a target. But it is not so in nature. Everything is partially polarized. Then, in that case, the S matrix itself is not enough. We need to go beyond and find out statistical description of the S matrix. And here is what we come up with, is that we go from a coherent measurement, from a scattering matrix measurement, to an incoherent measurement via what is we have a vectorization of the matrix, which is a scattering vector. We can do it in various different ways, but the two are the one which has been used as the two basis matrices, the Pauli and the Singh. Now, this is the information what we have for target information, so coherent target information. Here we go into the incoherent measurement. So this is again where we start with. Now, this kind of representation can be made very well that we can measure a coherency matrix, which is the incoherent measurement. This is with an ensemble average, this angular bracket, or the covariance, or we can also have a real representation of a 4x4, which is called the Keno matrix. In between sits my 2x2 complex scattering matrix, that's the Sinclair matrix. So the thing is that it's very nice that we can go from one to the other. We can go from a coherency matrix. These are only simple similarity transform over here. We can just do a transformation from a T to a C and C to a K and so on. It can all be done. And you can also go back from here, but you cannot go back from here to there because since you've already averaged, there is no single scattering matrix for an averaged out information over here. So this is where we start with analyzing the full polarimetric SAR data. Just to give an example of an area, which is the San Francisco Bay Area, which is an optical Google Earth image, and this is what we see as a false color composite image. If we want to see them channel-wise, instead to see them in terms of components, which are in terms of the HH plus the VV, the mod of that, the HH minus the VV or the HV component, we see that these corresponds to typical scattering mechanism, the odd and the even and the random kind of. So that tells you about that this is useful to characterize scattering mechanisms of a target. Of course, not completely, but as a first-hand information. We are just getting from the data this information. This is the area of from where I come from, Mumbai. So we can see that the urban area is much more prominent in the even bounds case, where it's HH minus HV, whereas you can see the water more prominent in the HH plus VV. Over here, the volume is more, this is a national park over here. It is more in the random volume case. This gives an impression that this is the first approach or the first information which we can get, making this false color composite, which themselves are mechanism characteristics. But now, till now, we have been talking about all in terms of a particular polarization basis, which is the H and the V basis, the horizontal vertical basis. But not that it is always true that we have to stick to this basis. We can change from, because since we have a full polarimetric measurement, we can go from one to the other basis. And we can go from an HV basis to an LR basis to any other 45 135 basis. The idea is that maybe in a certain other basis, you get different information which you might not get in any other basis. So that means it is useful to characterize information in all possible bases and to try to see where the information what you're looking for is optimal. There are very nice techniques of doing it, and people have utilized it a lot for different kinds of application. So this is what is important when you look into by changing the basis information. Now, as we talked about that, what is this dual polarimetric measurement is as what it is. We have seen till now that we have the scattering matrix measurement for a full polarimetric sensor. But if we just think a little bit, then the projection of this mesh matrix is actually the dual pole measurement. That means if we have a projection of it on 1, 0, this is the HV case. If we have it on the scattering matrix on the projection, this is just the vector which corresponds to the dual pole case. So that means the dual pole data representation is actually a projection of the full pole matrix into a vector 1, 0 or 0, 1. So it's either. So that's very important, because from here we are then able to find out Similarly to what we have for a 3x3, we can also form a 2x2 covariance matrix. This is also called the Jones matrix in some literature, but in the literature of radar, we just call it as a 2x2 covariance matrix. And this is what is very useful in analyzing all the data which are available from a dual pole mission, the Sentinel, for example. If we go to the compact measurements, the compact measurement is a little bit more trickier because again, now we can also represent it as a projection of the S matrix, but the projection is of this kind of a vector. So this is the projection of the S matrix on this vector, gives you what you have as the compact measurement. I mean, it's a circular transmit and a linear receive kind of thing. Over here, then also we can form a C2 matrix, a 2x2 covariance, and this can also be written in terms of the well-known Stokes vector ellipse, which then again allows us to extract information from here for different applications. Now, this is what we talk about, the representation of full polarimetric SAR data, dual polarimetric SAR data, and the compact polarimetric SAR data. Now, moving on from here is that the target characteristic concepts. Now, there has been so many different concepts which has been there in the literature, and each one of them has its own merits. So if you are looking into the core and target characteristic, that means only from the measurement of the S matrix. So the S matrix is then broken up into many constituent canonical targets, and then we are able to find out the target corresponding to the closest to which kind of canonical target. In this respect, we have the Pauli basis decomposition, as I've shown, is the most simplest, but of course it has its own flaws. Then came with the sphere diplane helix mechanism by Creuer. Then this is the non-reciprocal symmetric asymmetric by Cameron, and the symmetric scattering mechanism method by Tuzi. So this has been there for characterizing the single loop complex image for coherent measurement. We can also do that with very nicely with the signatures. Signatures has been used a lot in radar polarimetry for analyzing target. That means if you can have a copole measurement, we have the same polarization as a transmit and what you are measuring. So that means the space of all chi and psi, the transmit orientation and the electricity. That means this is the space, and we have a 90 cross 180. And you are able to characterize targets for the copole measurement, the trihedral, corner reflector, a dihedral and dipole, and so on. And you can also look into the cross pole measurement, which then allows you that for a single pixel, we have a large space. And this space can be utilized to characterize different targets, different canonical targets with the one which is measured from the full polarimetric radar data. So going from here is what has been studied a lot in the literature is the decomposition concepts. The concept comes from that we are trying to find out from each single measurement, we are trying to form a distributed or an average target over here. So we are forming the coherency or the covariance matrix from each individual Sinclair matrices. And this is what we utilized for the target decomposition. And of course, there are various different techniques in which they can be done. And in this, there are two different, I have put them as two different ways of doing it. And I have put them as one as the conventional setting. And I'll put the other one as a non-conventional setting. I'll clarify them very shortly. Now, I talk about this conventional setting. So what we have seen that in the coherent case, we are only utilizing the scattering matrix S for characterizing pure target. And from here, we have found out the distributed target by ensemble averaging over pixels. We get coherency in the covariance matrix. And this is where we start from. The first one is what is called as the model-based decomposition, has been there since the starting from the decomposition given by Freeman and Durden. And after that, there has been a lot of improvements and new concepts, and it is still there. It's been still going on. The research in this direction is very, very active and is still going on. The other one is what we call as a more mathematical description or an abstraction is the eigenvector eigenvalue decomposition given by Cloud and Potier. Now going into the model-based decomposition, as I mentioned, well, of course, there are many of them, and you can see them in the literature. They are coming up maybe with more and more modification, more and more new models, more and more powers, more properties, and so on. But I just want to give only the first three, which is a Freeman-Durden, the Yamaguchi four component, with the rotation of the coordinate symmetrics. And over this, as I mentioned, people have put into more efforts, and still people are putting in a lot of efforts to find out more different components, more different ways of characterizing targets. As you can see that there has been improvement as you can see that over here, the urban area was not properly characterized. It was made better with the change or introducing another another target over here, another model over here as an helix with a four component. So this was further modified with a transformation of the original matrix and then applying this over here, which then gives further better information. But as I mentioned, that this was also not enough, but then people made more varied decomposition. Going into the one which is the eigenvalue eigenvector decomposition, of course, it started with the characterizing more in terms of the scattering mechanism or the scattering type parameter. The one which is given is the more known in the literature as the cloud alpha parameter, which is useful to characterize scattering mechanism for a target, which is varies from 0 to 90. 0 means a trihedral or for a single bounds, and you have over here for an even bound. So odd and even bounds in between, you get dipoles and so on and so forth. So it's a continuous scale in which you can get the scattering mechanism. This is cloud alpha, but you can also come up with a measure of the randomness, which is in terms of the entropy parameter. So you can see that the entropy is quite low when you have calm water over here, and over the area where you have forested area and urban area, the entropy is quite high, which is very natural over here. So with these two parameters, the scattering type parameter and the scattering randomness parameter, they're able to characterize it in a plane with 8 different clusters. And this is very physics-based clustering. And this gives you an information about the scattering type information along with the entropy. So this H alpha segmentation plane gives an information about this about these 8 different clusters, and they can be used as a starting point for various different other applications. Now, apart from this, there are several new advances have been made in the literatures, and some of them have been made in our group, and we are still continuing in this direction. One of them is the one which is the model-based decomposition, which uses statistical information theory. This was the first time which it introduced statistical information theory in radar polarimetry, and this is now available in the Pulsar Pro platform, and it can be used for full polarimetric decomposition. And with the results of some of them are something like that. This is again an image of ALOS 2 image of Barcelona. This is the poly RGB. This is the Y4O. This is the one which you have from this new decomposition, which is the one which introduces the 4 component along with some statistical information, theoretical information. This is again the ALOS 2. This is the one, the previous. This is the one which you have with the new decomposition. Now, this is what we have seen in the conventional setting. Now, it's becoming much more clear that why it is conventional, because I'm talking about what has been there in literature as a model-based and an eigenvalue-based decomposition. One is characterizing more with the model, the other is a mathematical abstraction. But what we go now is something like a non-conventional. The first one I talk about is the factorization. So I don't call it as a decomposition, but rather a factorization. So it is not summing them up, but it is factoring them out. So this is a new way of looking into, and we have made something called a unified framework with the help of a geodesic distance measure over the space of the real Kano matrices. And utilizing them, we have able to come up with parameters which characterizes target similar to the one which has been given by cloud alpha. We name it as alpha, a geodesic distance measure. We can give it for the alpha, the scattering type mechanism, the scattering symmetry, asymmetry measurement, and similarly as what you have seen in entropy, it is the purity measurement, just the kind of an opposite of the entropy. This is called the purity measurement. So this is again coming from the measurement of full polarimetric measurement, but here we utilizes the Kano matrix, but it can also be utilized for other covariant structures also. It utilizes it and come up with this information of scattering type mechanism, symmetry, and purity. Utilizing them, if we try to analyze this kind of a scenario where this is for coherent target measurement, this is for ships over this calm sea area, this is for Aralos 2, I'm able to characterize the different kinds of dominance of the scattering mechanism. So which kind, so these are the canonical targets, starting from dihedral, nanodihedral to right and left helixes. I'm able to characterize which is the one which is dominant. This is the second dominant, this is the third dominant. That means it allows us to not only find out the mechanism, but also find out the dominance in the mechanism as we are factorizing it depending upon their dominance. If we go for the incoherent, this is the area of San Francisco, we are able to see that here we are also finding out the scattering type information. Here it is more dihedral and narrow-dihedral. This is dihedral over second mechanism. And on third onwards, it becomes noisier and noisier. You can go on and find out that it's really noisier, which gives me information that not only we are able to characterize the scattering type, but also with the dominance. With it, we can also find out which are the information, the scattering type information in a particular image. So we can also cluster it basically in 4 clusters. 4 clusters giving the information of the scattering type. Along with that, as which is a normal trend, is to give the power information, we can also give it as a power information. So that means we are able to characterize it in terms of the properties of the target, the property of the scattering of the target in terms of some descriptors. We are able to find out the dominancy. We are also able to give the power information at one go. This is in one framework, everything. Moving on to the next non-conventional type is that first one, what we have seen over here is the model-based decomposition. But similarly, we have proposed, this is very new, is model-free. So we don't need any model. Models have their own limitations because they are non-unique, first of all. So you change your model, the decomposition becomes different. And also there are other certain difficulties or challenges which are there in model-based decomposition, which I'll not have time to discuss over here. But so that's why we bring in something which is a model-free decomposition. That means we are not dependent on the model, and this is one unique way out. And this is what we have utilized, that we have utilized a long-standing information which is called the Barakat degree of polarization, the elements of the coherency matrix, and along with that, we generate something as a scattering type parameter, and over there we find out the scattering powers. Why it is important? It is model-free, it justifies uniqueness. So the scattering types and the powers we find out simultaneously. There is no hierarchy, there is no criteria, nothing at all. There are no non-negative powers. Non-negative powers are a big challenge in the model-based decomposite. It has still been there, and some of the methods have tried to avoid it, but have to pay the price on that. So there is no non-negative power over here, and this is much more robust in the sense that this is equivalent for different acquisition mode. You can have it for full pole, you can have for compact, you can have for dual compact, which is kind of a TerraStar mode, HHVV mode, and it can also be extended to the bistatic mode. The same formulation, the same idea we can make it for different acquisition mode. And all these feature descriptors which we get over here are role invariant in nature. So with this, I'll just give you some examples over here. This is an image over an L-band allows 2 for Tokyo. This is what we can see with this parameter, which is called as the scattering type parameter. It varies from -45 to 45, 45 being odd bounds, -45 being even bounds. So something similar as you can see with the alpha, but for a different scale, but also different. It gives also different information. And with this, again, we can find out the power information directly over here. So no models over here. No models has been used, only the scattering type information and the power. This is an area which is the LA area from this is an L-band UVSAR data. You can see this is an urban area. This is the forest kind of an area. You can find out the scattering type information and the power simultaneously. So you don't have to go from an eigen decomposition for finding out the scattering and going to a model based for a power. You don't need that. In one go, you can find both of them. And it's just one step to do that. So this talks about some of the newer trends or the newer theoretical developments which has been there. As I mentioned, we call it as non-conventional because the first one we talk about factorization, not the conventional decomposition, and the next one is model free. So this gives a more flexibility in characterizing targets for different kinds of application. Move on over here. The last part we talk about some of the applications. I'll talk about only two possibly over here in agriculture. So in agriculture applications, we are dealing with a lot of research components over here, but mainly we are into crop classification and biophysical parameter estimation. These two are more, we are more concentrated on at the moment. This is an area which we have a study area. This has been a long-standing study area for all our missions. This is mostly the radar set acquisition over here. It has been going on for many years now. This is the area which have paddy cultivation over here. And we can see that this is what we have developed as what we name as the generalized radar vegetation index has been developed. And we can see that it characterizes much better than the existing radar vegetation index, which has been their literature, because this area, as you can see, is paddy. And over here, this is in 11.6 over there, which was, there was no paddy over here. This was there was standing water over here, but by this time there is this paddy growing stages, but the RVI is not able to capture anything over here, but the GRVI has already captured over here information over here. And over here, it is still not able to find out anything over here. We have rice paddy grown over here. It can be seen over further in the temporal series that the RVI is unable to capture on both the sides of this is the river. On both the sides you have transplanted and direct seeded rice, two different kinds. And in this case, you are unable, RVI is unable, whereas the generalized vegetation index developed by us is able to characterize it much better. So this is what we can see as a movie where we can see the increase or the change, the dynamic change of the GRVI over this area where we have different crop types. And you can see that when you have from the first date, which is this 5th, there is nothing over there. It was very low. It increases rapidly and goes to a saturation. So we have been also using a lot of this analysis ready product in the PI and biomass map. This is what we intend to, and we are also working towards it. The dual polar vegetation index has been also given by us. So we have, we have over here two products. One is what we have an SLC product. So this is what has been given as the DPRVI is nothing but it's a combination of the degree of polarization and a degree of dominance over here. And if you can see in this as a plot, as a polar plot over here, this can be utilized to characterize targets. Over here, this is the we have a completely random case over here, and you have over here a completely pure case over here. So it moves from here to here, and with this you can see the dynamical change of this type of change in the crop pattern over here. And this has been utilized for different studies for, and this can see that we are able to well characterize with the DPRVI the characteristic of the growth stages of different phenological stages of a canola over here. This is also the bottom row shows about the Sentinel-1 DPRVI for rice growth dynamics over this region in India, which we just showed in the previous slide. So this is the SLC, as I mentioned, because you need the full, as I mentioned, you need the full covariant structure. You need the covariant structure to make the degree of polarization, and then only you can do that. But now we also have a GRD product. We have the GRD DPRVI, which is given in the similar formulation, but instead of the degree of polarization, we have the copole purity parameter and the degree of dominance parameter, which is nothing but given in terms of the ratio of the VH and the VV over here. And this is again utilized. We have utilized it for soil moisture estimation in a recent study. So we have both for the SLC and also the GRD product, which can be very nicely used and have been utilized by many across the globe for different applications. Moving from here to the urban studies, we are working a lot on urban growth characterization, urban area mapping, and so on. This is one study which shows about the temporal differences. And this study is done utilizing, as I mentioned earlier, using the geodesic distance-based measure on the Keno matrix. Here you can see a temporal change which has happened because of the construction. And as you can see that we are able to utilize a descriptor which is measured on the Keno matrix of two dates, different dates, and you are trying to find out a similarity measure, a dihedral similarity measure, because as we know, dihedral is a prototype of urban structures. So with this, we are able to characterize urban growth, urban changes, and with this, we are able to find out what is called as a radar built-up index. And with this built-up index, we are able to just do very simple thresholding, and we are able to find out the urban map. This is a binary map of non-urban and urban. But this is again utilizing only full polarimetric data and utilizing the same framework as we discussed before, is the factorization framework. We have also gone into a little bit of image clustering. So this is clustering from the data itself, from only the scattering physics. As we have seen before, you have the H alpha. You will also find out the similar one with an alpha GD and the purity space. And this is the defined purity space. And we have defined certain region based on the scattering type of characteristic. And with this, we again can form an 8 clusters. And this is the area of Mumbai, and we can very well see that it has well clusters all the areas, the water body, the urban area, the agriculture area, the forested area, of course, over here, and some kind of a wetland type over here, basically. So this is, we're able to characterize it very good with these 8 clusters, but with this PGD or the purity alpha GD space. With only segmentation between dependent on the scattering of physics. This is again, we have done it with the theta FP parameter, as we have shown before, the theta FP, which characterizes the scattering type information and the entropy plane. So this is for a full, and it can also be shown for a compact. So they are almost in a similar way, but of course they occupy different space. And we have also can find out over here 12 different clusters coming from low entropy, medium entropy to all different kind of scattering over here. This gives an information about the segmentation, but it is only based on the physics of scattering. Similarly, as I mentioned, that we have also made something which is model-free decomposition. If you utilize those model-free concept, you can also come up with, we have also come up with a segmentation which is based on the physics of scattering. And here you can find out much more finer classes. So over here, 24, because it introduces not only the even, odd, and the diffuse, but you also have the asymmetric scattering in terms of the helix. So this is much more finer much more finer clustering mechanism. So these are the new developments which have been there, which have come up from our lab. So we have a lot of these have been now contributed to the ESA SNAP platform. You can see that the radar weightation indices for dual, for compact, and for the full pole are now all available in this SNAP toolbox. The polarimetric decompositions, the model-free decomposition, the 3-component and the 4-component, there are 2 versions of it, are also available now in the SNAP toolbox. The compact decomposition, which is from, as I mentioned, came also from the model-free, because as I mentioned earlier, it can be done for full, it can be done for compact, and also for the dual co and the bistatic. Here for the compact also, it is also there available in the SNAP toolbox. So this has all what has been done in the framework of different studies in the lab. We have all given it for the use for the community, and they are all available either in Pulsar Pro or SNAP toolbox for use. Because we believe a lot in the reproducibility and replicability of our research. All of these are available either in all Python codes, Python packages. We also have a Pulsar tools, which is a plugin, which can also be utilized. It's a plugin in QGIS plugin. It is now available, and it can be utilized for all different methodologies which have been developed in the lab for different analysis. So where are we going from here? That we know that we have upcoming many missions coming up, and our own NISAR is upcoming. And with that, we have a lot of data to process, of course. And there will be, of course, these Earth engines will be there, starting from all different But the idea is that we have to now move all these things to the platform where we need to have a seamlessly, we can put them into these Earth engines so that all these things can be done over larger areas. We have done certain work in this direction, and we are going ahead. And as you can see some examples over here, that this can be all incorporated into some Earth engine for doing it for more dense data, more large area data, and so on. Some pipeline which has been there. Some, of course, for some who wants to use free SAR data, there are very nice data sets available from different sources. There are some very nice books available for radar polarimetry, from basics to applications and so on. And I would like to tell that about this new book, which is the Radar Remote Sensing for Crop Biophysical Parameter, which was written by my former student, me and my colleague over here. This talks about all different advances which has been made in radar remote sensing for crop biophysical parameter estimation. Before ending, thanking all the collaborators for being there, and with the help of whom we have been able to do this kind of work, and we are continuing this collaboration. Thank you for your patience.
Thank you very much, Avik, for a very thorough presentation.
Thank you very much, Nicola.
Thank you for this nice presentation.
Thank you.
Yes, we have a first question with Wang.
Thank you so much, Professor Avik, for your excellent presentation on the SAR polarimetry. Actually, here I have several questions to discuss with you. And the first is about your non-conventional polarimetric decomposition, for example, the model-free decomposition. So in that case, how can we differentiate the different scatter mechanisms if we not integrate the modeling process in this? And also in the model-free decomposition, in addition to the scattering mechanism and also the scattering power, can we retrieve other additional parameters from this algorithm? This is the first question. And the second question I would like to know, for example, the model-free decomposition. So the starting point is S matrix or the T matrix or C matrix. So which matrix as the starting point for the model-free matrix? Because in the literature, I remember, for example, even for the traditional decomposition, when we use the C matrix or T matrix, sometimes the results are different. Even there is just a similar conversion between the T and the C, but sometimes the results are different. That's my second question. Thank you.
Thank you very much for very nice questions. Yes, first point is that, see, when you talk about model-based decomposition, so what you are trying to do is that you have a measurement of you have an incoherent measurement, and you are trying to fit into with 3, 4, and then you're going on over there. So of course there's a limitation. Of course you are going on because at some point of time you will be there will be no there will be more independency, orthogonality will be lost, kind of thing. So you are trying to fit into over there and trying to find out the coefficients which are the scattering powers information.
Yeah.
So this is a discrete way of doing it. So let's say if you do a 3-component decomposition, you still have an underdetermined equation. You have to bring in an auxiliary information to solve it. 4-component, you go into more complications, and after that you go into branching conditions and so on. So what you are doing is you are trying to fit into the T matrix with this model, but then putting many constraints over there.
Yeah.
The very good part is that why people are utilizing a lot is because of the ease of understanding, because since it is a model, now you know that what you are giving and what you'll be expecting out of it. So there is a transparency kind of thing. So that's why people are more interested in fitting into with a model. But of course, we have to be very careful that when we fit into this model, we tend to overdo it, because we might bring in models which are already there in some other model. Let's say we bring a model A and a model B and a model C, but maybe model C has already some portion which is already there, information which is there in the model A. So because there is non-orthogonality information, we are not able to characterize that. So these are the typical problems which has been there in model-based decomposition. People have solved it in various different ways, but still the intrinsic problem of that, how to fit into different models, people have tried to make remove elements to make a more symmetry assumptions and so on and so forth. I mean, I'm sure you know about them, but again, those are transformations where you are trying to get to something which actually was not measured, basically, because you are trying to go into a measurement which was not measured, basically.
Okay.
So in this model-free decomposition, what you see is that I am utilizing only the coefficient, only the elements of the covariance of the coherency matrix, and I'm using a parameter which talks about only the purity of the scattering, which is the Bhattacharya degree of polarization. But careful is that the Bhattacharya degree of polarization still does not characterizes the entire polarization characteristic. It only measures a part of it, because the Bhattacharya degree of polarization actually directly comes from the optical polarimetry. And if you see there, it is only measuring only one frame, only one characteristic of the plane. It doesn't measure the plane information. So it's from optical polarimetry. But in full polarimetric measurement, it still gives you a very good information about the purity of the state. And hence, we utilize this purity measurement along with the scattering parameter, the T matrix element, to first come up with an element or a descriptors which tells you about the scattering type information. And if you see these descriptors, the descriptors exactly the elements, I mean, after fitting it, these exactly are the elements which comes from the Hoynen parameters also. So it's actually reflected from the Hoynen parameters, because it directly tells you about the scattering mechanism. And this scattering information we use to just convert it into power, because since this scattering type information is a continuous measurement from -45 to 45, you can directly transform into a geometrical measurement. So you just make a geometrical measurement out of it and multiply with the span. So what you have is anything which is towards +45 is going towards an odd bounce. Anything which is towards -45 is going towards an even bounce. The more it goes towards -45, the more pure even bounce. It goes towards 45, the more it is purer odd bounce. So you get a whole spectrum of it. You are not fitting into, but you get only three measures. You get only three powers. One is the odd bounce, the even, and the diffused, because it is not volume, because there is no model. So you have to be careful with that. It is a diffused, so I will call it as a diffused, not a model. So that's so that clarifies your thing. It's okay.
Yeah. Thanks.
Yeah. Sorry, your second question was.
Yeah, my second question, because sometimes when we do the decomposition, sometimes we start from the P matrix, sometimes we start from the C matrix. But I remember that I saw a paper, it is said from T matrix and from C matrix, the results sometimes are different. Although there is only a similarity conversion between the T and the C, but sometimes the results are different.
Yes, even though there is a similarity transformation, you have to be careful when you equate those models. When you equate those models, they have to be, because mostly those you have seen, mostly those the criteria or mostly those things are given from a T matrix measurement. But some of the criteria also come from C matrix measurement, because if you see, when they talk about reflection symmetry, it comes from the cross correlation, which actually is a measurement from a C.
Yeah.
So you need to be very careful when you put into this constraint. These constraints are actually carefully and properly put, because people try to sometimes mix it up a little bit. They take things from here and mix it over there. That's why there is a problem in those matching of the answers, basically. But actually, you can do it with both. I mean, mathematically, it is justified.
Yeah. Okay. Thank you for your.
Thank you.
Thank you, Wang. And Avik, if you still have like a few minutes, there would be like another question from
Sure,
Banu,
of course, I'll be happy.
Thanks. Go on, Banu.
Hello, Professor Avik. I'm Bhanu Prakash. I'm working with Professor Khalifa Goitz and Professor Ramata Magaji. I'm working on soil moisture retrieval from C-band SAR data. So I want to ask, you have much experience in working with C-band SAR data for soil moisture retrieval. So I'd like to ask, what are the challenges you're expecting from C-band radar data when you, especially when you have vegetation growth on the soil? So what would be the challenges, and what can we deal with it?
Yes, that's always the question, that how can you deal with that? Yeah, so there is a paper which is just accepted 2 days ago in transaction. I will ask my student to send it to you. This is a work which we have done with our collaborators. So in this, what we did is basically you take the measurement and try to remove. So it is the soil moisture over cropland. So the idea is that you take a volume model, whatever that model can be. Of course, it depends upon your expertise of what kind of model can you fit into that kind of a crop. But in general, you can take any random volume case, and we try to subtract it from the measurement. So basically removing the volume component. But it is a bit tricky, because in the sense that if you remove it, you remove the subtraction should also give you the product which you can again work with, because it has to have it should be Hermitian, positive, semi-definite, and so on and so forth. So you need a trick to remove it properly, so that you have the residue matrix to work with. Now, this residue matrix will be composed of it is a two rank 1 matrices. So that means it will have two components which comes from the target measurement. So it's a two rank 1 matrices. Now, let's say because it is crop, so it is a soil over crop. So you have removed the effect of crop with the volume model. So basically what left out is the soil component. But there are two measurements you already have. So people also try to model a dihedral, but we have not done it because assuming that there is no dihedral mechanism. But again, it's an assumption only. But let's say if you are not able to completely remove it, there could be a dihedral. But let us forget about that. Only what we have is a surface model. Now you can then model the surface with an X-Bragg model. Now when you model under an X-Bragg model, then you can invert from the X-Bragg model the permittivity. So that's what we have done, and the results are quite interesting and quite good. But again, the point is that if the vegetation, of course, no, the vegetation is very dense, then, well, even if you do that, I believe that there is no signal coming from the soil. So, well, it is not justified to do that. I mean, of course, mathematically, you can do so many things, of course. It is there. It is very nice to do all these things. But the signal should come from the soil. But if it is soil, if it is too dense, no, it's not. Sparsely to a certain extent with a C-band. So you have to be careful in which area you're applying it. If it is too dense with a soil, no, I don't think it's a right way of doing it. So
okay, thank you.
But I can share the paper. I can share the paper. You can have a look at it, and you can discuss with the authors if you want also.
Thank you so much, Professor.
Thank you very much. I wish you all the best for your work.
Thank you, Professor.
Thank you, Benu, and thank you, Avik. Est-ce qu'on a une autre question, ou Khalifa, si tu as un commentaire avant qu'on finisse la séance?
Peut-être j'ai une petite question. Avik, I found GRVI is a very nice index, and did you see some limitations over the areas where you use it, where you tested it? What are the main limitations related to it in the areas you use it?
Yes. So the limitation, I mean, we have not utilized a lot of it basically because we had only quite few data, I would say, to utilize it. But yes, that's a very good point, is that we have seen, as you can see in the images also. So the rise of it is quite nice, but it saturates quite fast because of the thing that if you see the formulation of how I did it with the GRVI, is that it is the measured, whatever you are measuring, and with a model. Actually, it's a kind of a distance with the geodesic distance with a model. And as I just answered to the question of Dr. Wang, that since this model is assumed to be a random volume model, then in very C-band cases, this is saturated for up to over just after some growth stages. So after some, it is just, it's a flat kind of thing. But when it is growing stage, it captures very nicely. That's I have seen. So it's there. But after certain phenological stages, it becomes, and that's also what we can see also. That's an excellent trick, because we have also seen that, but we have not gone beyond that to check for a lot of different crops, kind of thing.
Okay. Thank you very much.
Merci, Khalifa. Thank you, Avik. So thank you very much, Avik. I think we're gonna end the session now. And thank you very much for your time and your presentation, and for the time for answering the questions. This was really a pleasure to have you for our MIDI maps.
Thank you very much. The pleasure is mine, of course.
Thank you very much.
Et merci à tous d'avoir assisté.
Merci.
Et puis on se retrouvera avec un prochain minimap dès la semaine prochaine. Là, on en a deux qui s'enchaînent, avec le professeur Norm O'Neill, qui nous présentera une de missions sur lesquelles il est impliqué avec l'Agence spatiale canadienne et la NASA. Fait que ça, ce sera mercredi prochain à midi, en présentiel pour les gens qui sont à Sherbrooke. On aura de la pizza à partager. Et puis, ce sera aussi en ligne, on fera ça en mode hybride. Et que merci à tous pour avoir été ici et puis à la semaine prochaine pour ceux qui seront là.
Thank you very much, Avik.
Thank you very much,
Thank you.
Avik.
Thank you. Have a nice day. Thank you. Bye-bye.
Have a good night.
Bye-bye.
Bye-bye.